since 2018. All they have to do is point a phone at you. They will connect with your biosensors and do whatever they want to you under the skin. We're here with the IEEE, and we're going to read a beam steering antenna for 5G mobile phones. For the first time, a beam steering antenna is integrated into the metal casing of a mobile phone, and this was released in 2018. The final architecture of 5G cellular networks has yet to be carved in stone. However, it looks as though millimeter waves, with their ability to obtain wider bandwidths, will play an important role in 5G, the next generation of mobile phones. The combination of these bands, along with directional phased array antennas, in which radio waves can be steered electronically in a desired direction, will constitute one of the key technologies in future 5G cellular systems. While there have been a number of research efforts that have demonstrated that these phased array antennas can be added into mobile phones using low-cost substrate boards, no one had demonstrated that it's possible to build these antennas into phones with fully metallic casings, as can be found in the high-end mobile devices from numerous manufacturers. Now, researchers from the Shanghai Institute for Advanced Communication and Data Science at Shanghai University in China have developed a 28 gigahertz beam steering antenna array that can be integrated into the metal casings of 5G mobile phones. The antenna elements and arrays are easily integrated on the metallic frame or casing of a mobile phone, which is more suitable for industry mobile phone design, said Danny Yu, the lead author of the research in the journal IEEE Transactions on Antennas and Propagation. Compared to all other existing works for millimeter wave 28 gigahertz band, this work is totally unique in such a sense that it is very close to what the industry is working towards at the moment. The antenna elements and arrays proposed by Yu and his colleagues are connected and controlled by a radio frequency integrated circuit transceiver. In this arrangement, the phase and amplitude of each element is controlled by the RFIC transceiver to achieve beam steering characteristics.
But you see, that's just their cell phone. They are going to get a hold of the wireless sensor networks, the body area network, and then they can steer those biosensors any way they want, which will very easily allow them, given that quantum dots can grab hold of that force and make those neutrons turn into those neutrinos, and oscillate and potentially rearrange your cell structure into something else entirely, without electromagnetism being a problem. What they are doing to people completely changes and alters their physiology electrically, biochemically, and they are doing it using biosignals for supervised bioelectric magnetic algorithms. That is literally electrocuting people under the skin, and they don't even know it, because they don't believe in their own anatomy. They literally have a phone, and with the right equipment in it, or an app that has access to the right software-defined networking, in order to select your channel allocation for the human involved. And they are targeting humans. Their paperwork illustrates clearly where the capacitance for the system is. They brought the internet from dial-up to broadband, and they've brought the internet from broadband to body area networks. They just didn't tell anybody.
Making fully digital beamforming for radar and electronic warfare applications a reality. While the basic physics of beamforming were first identified more than a century ago, it wasn't until the past 2 decades that advances in supporting technology enabled the rapid expansion of the types of application that can take advantage of this technology. As early adopters of beamforming technology in the 1960s. In the 1960s, aerospace and defense organizations have a lot of experience using the initial large-scale active electronically scanned arrays, AESAs, for military radar tracking applications. As a result of the innovations led by military organizations for several decades. Commercial applications such as weather detection and radio broadcasting were able to benefit from the use of beamforming technologies as well. But today, the operational frequencies of the targets of interest are increasing. As a result, the wavelengths of these signals are shorter, which means the density of the array is increasing since antenna spacing needs to be set at 1/2 of the wavelength. For example, 25 gigahertz, the wavelength in free space is approximately 12 millimeters, leading half-wave spacing for antennas of 6 millimeters. And the denser the array, the more important it is to be able to steer beams to avoid interference, especially when transmitting signals. This article provides a brief overview of how the technology used inside arrays, such as passive components, have evolved to allow for the possibility of fully digital beamforming today, and how RF designers can overcome the challenges associated with designing a fully digital array that can be used for military applications. A brief overview of beamforming options. Over the years, beamforming technology has evolved significantly. Configurations have changed from traditional large analog applications to hybrid digital/analog approach, and to the introduction of fully digital arrays in the past decade. While digital beamforming is opening a new range of possibilities for phased array technology, it doesn't mean all phased array applications should make the shift to digital. Instead, there are multiple considerations to make when thinking about the best beamforming technology for your application, including the number of beams required, power dissipation, and budget. So, they shift the phase. They shift the way the beam allocates by channels. They shift the way the beam connects. They have backscatter. They have a lot of different things they can do. And here is figure 1. The key differences among analog, digital, and hybrid beamforming are the number of ADCs in place compared to the number of antenna elements and where the beamforming takes place. What does ADC stand for? We're going to Google. ADC in radio frequency. RF analog to digital converters directly sample high-frequency analog signals, ranging from hundreds of megahertz to several gigahertz, and convert them into digital data. I always say, if you don't know something, Google it. Now back to what we were reading. The diagram in figure 1 provides a simplified overview of the key differences among these three beamforming approaches by showing the radio frequency path to the single amplifier and ADC pairs. More specifically, with analog beamforming, one ADC is used for the entire array. This means that the adjustments to the array with a simple software rewrite for all the antenna elements is limited to the functionality of what that single ADC can do. Software-defined radio. They have been able to do this since wireless with the Navy in the late 1800s. They just hid it from everyone else. And they are beamforming and beam steering. That's how the terahertz bullets and the duplicate housing structure for the kill box works, which they've had since the 50s and 60s. It hasn't been as prevalent as it is now due to the metamaterials being in the air and the air molecules that are more metallic, but it has been there for a long time. Fully digital beamforming is kind of like software-defined networking. They can just change it with the software in the air. As the signals the military is interested in monitoring are evolving to higher operational frequencies, there are a number of benefits that can be achieved by using fully digital beamforming for some applications. First, multiple simultaneous beams can be detected and transmitted, since beams can be split in multiple directions at the same time. Plus, if you want to change the direction of antennas in the array when sending or receiving signals, that can be done much faster since each antenna is individually controlled through software. Additionally, dynamic range is improved as more ADCs are added to an application when the ADC is moved closer to the antenna element, like it is in a fully digital array. For example, if an array has 256 antenna elements, and each element has its own ADC, the dynamic range is 256 times greater than it would be in the same analog application that has one ADC for all 256 elements. Therefore, detection is more flexible and powerful, meaning more signals can be detected. Finally, since the job of each antenna element is software defined, each element can be individually controlled and tuned, which means one system can be used for multiple missions. When one array can serve as a multifunction device, with antennas pointing in different directions, a radar system can monitor for signals coming from multiple directions. Therefore, the limited space in some environments, like on a ship, can be used more efficiently while also achieving more comprehensive radar coverage. While these benefits make it clear that digital beamforming is an excellent option for military applications, the physical size constraints for the electronics and passive components needed behind every radiating element, especially for high-frequency applications, make these systems challenging but not impossible to design. Let's take a quick look at how to overcome these challenges today. In the topics section, this is your radar/LiDAR systems, electronic warfare, electronic equipment, RF microwave, surveillance and security, threat location, targeting and surveillance, transmitters/receivers.